So today I would like to discuss triangulation sensing, how to recover the source location from diffusion fluxes. And so this is the third part of a series of classes about morphogenetic gradients, a computational principle. We saw previously how a gradient can be generated, how by diffusion, how cells can found themselves into this gradient. And today we are going to discuss some principle of navigation based on the ideas that the cell can find the location of a source based on the principle that we've called triangulation sensing. So suppose you have as a model of a cell a disk which contains 3 windows, and this cell is embedded into a gradient field where you have here a source, and this source generates diffusing particles. And so this is a snapshot of the positions of these diffusing particles. And what we have implemented here is cells that can move, and each time, and the principle of moving, it's able to compute or estimate the number of these round molecules here that I'm highlighted in red, that enters into this one of the 3 windows. And by comparing what happened in receptor 1 compared to receptor 2 and to receptor 3, we take the maximum, and the maximum will basically give us the one of these direction. There are 3 possible directions, and then what we do is we estimate the center of mass, and as a result we have here this path. And what is interesting, we go from A to B by just increasing the number of particles, or how steep is the gradient, and as a result we get a trajectory which is has much less large variation, and this is going to be quantified in a paper that we will publish in the future. So now what I would like to discuss is the general principle: can the position of the source be computed from the flux of Brownian particle to few windows? So again, you assume here that you have a source, and this source can emit Brownian particles represented here in this gradient field, and these particles arrive and can be detected at each of these windows. And suppose, so the fluxes is the number of particles. So the fluxes at each particle, let's call it K, which is the number of particles per unit of time that arrives. And so we are interested in, suppose we know this phi K, can the cell be able to reconstruct the source S? And so for this we can formulate the problem as a solution of a partial differential equation, which is basically the diffusion equation. When particles start at this position x0, they cannot penetrate the cell in general except at one of these small receptors. And so at steady state we have a resetting. Suppose each time a receptor disappears, it can be created with a delta Dirac with the same condition as we discussed. Then we can estimate the probability flux into one of these receptors. So suppose here we have 1, 2, and 3. We calculate, let's say, the flux, let's say, suppose K equals here 1. We calculate the flux at 1, and we normalize so that the probability is 1. So suppose now I will show you that we can calculate pK, and then the general question is, suppose P1, P2, and P3 are known. Can we recover the position here x0 of the source? So to do this, one step is to use what is called the Neumann-Green's function, which is a solution of this Laplace equation, Laplacian J equals delta Dirac, and we take here the GDN equals 0 over the boundary. So note that is an external problem. For the internal problem, this equation has no solution, but for the external problem, so suppose here we are outside the plan, then we have this following solution. Or if we have here a disk and we are not inside but we are outside, so we have the same equation, and this is a solution which can be found as usual using the image charge. So here this is the image charge, which is, if you have x0 here, you have here this plus x0, which is the opposite, and here we have to take the power with respect to the circle of radius r. And so the solution of the previous equation can be found by using this Green's function here, but this Green's function do not account for this boundary condition p equal 0 at each of the window d omega 1, d omega 2. And so this is why we need to have here a correction, which is called a boundary layer correction, and we have here this constant to be added. And so the methods is here the classical match asymptotic method. And so again, in the outer solution here is this Green's function that we have to write this way. And if we magnify what happened in this layer close to the window, and this is magnified here, we use the general solution of the Laplacian equation, which is log of x minus xi, and divided by the length of the window, epsilon. And we have here a coefficient that we need to find. So the solution can be written of the form p equals the outer solution, which is the Green's function, plus the sum here over the windows, plus the constant c that we need to find. And so to do this, then what you need is a condition at each of the window where the solution should look like the boundary solution. And so when you do this, this term here for I equals j actually we have to sum over everything, but I equal j will disappear, so this will be equal to 0, and that's how you get here each of the equation which are exactly calculated at the position x equal xj. And we need to have here this normalization condition. And so we have exactly a system of n+1 equations with n+1 unknown, which can be solved and has a unique solution. So this is an example here in half a space and in a ball, where the solution can be written in general with this expression. And then we have to replace, as I showed you 2 slides before, that we can have the Green's function for each of the 2 cases. So since in that case p1 plus p2 equals 1, we just need to calculate one of them. And so now here is the question that we're asking. Suppose p1 is known, we know these fluxes of this flux probability. Can you find here x0? And so in general, in dimension 2, since x0 has to have 2 components, one equation is going to be obviously not enough. But we can see from this that the solution, the curve where x0 will be located, is going to be a circle, because this is the power of a point with respect to the point x2 and x1. And then we have to solve basically and invert this equation. So what we have been developing, so this is the solution. As you can see here, we have here x1 and x2. And of course, when p1 equals p2, basically, as you imagine, you need to have each of the 2 holes receive the same flux, so you have a degeneracy, and the solution can be positioned anywhere on this axis. And then by varying this probability, you see that where the source can be located in this on these circles. So in general, if you have 2 point 1 and 2, I mean, this method allows you to estimate the splitting probability. So for example, if you vary one of the angle, you fix theta 1 equals 0, this is what we did here, or theta 1 equals pi over 2, or theta 1 equals pi, and then you vary the angle theta 2 of the other small hole, and then you can estimate this probability here as we are showing here. So the main difference here was the location RL of the source. When L is very large, you see that you have more or less you converge to 1/2 because the two windows, they cannot distinguish much where the source is located. When L is very at a small location, then you can see here this difference. So we have here the expression for the different position, and this is normalized. I mean, this is normalized to the radius r. So this is L over r that we are exactly showing here. We assume that the radius is 1. So you can do the same. I'm not going to go much into details, but what happened, because you can calculate the Green's function when in addition you suppose the particles cannot escape and they are prisoner from a band of radius a. And I did this already in previous classes of simulations, and what was interesting here for this case is that suddenly, even if you go to a distance which is very far away, because it's very hard if the distance a is of the order of the radius, if you have a molecule moving, it's going to be very hard for this molecule to pass here. And so as a result, if you have two holes, one in the first half of the space, the other in this second one, then only the first one will be mostly receiving the particles. And that's why you can see that here the cell is able to distinguish left and right for a large distance of the source. So now I would like to go to the case of 3 windows. So this is a solution as we have written, which can be written as an outer solution with respect to the Green's function. And now instead of 2, we have 1, 2, and 3 boundary layer. And so how you get a system of equation, again, that you assume that near a window, let's say window 1, we have A1 is of the order of x minus x1 divided by epsilon. And so this is true for x close to x1. As a result, you remove this term and you plug here x1 in the rest of the term, which give you to the first equation. You do the same for the second and then for the third one. And then you have basically three equations, and we have 4 unknown. We have A1, A2, A3, and C, but then we have to use that we have a normalization condition. And so then you can actually resolve the system of 4 equations as I've done here. Here you reduce to 2, and then you finally get an equation for A1, A2, and A3 with respect to the discriminant of the solution, where dij here the difference between xi minus xj. And so again, if you assume that you have a specific geometry, here we have half of the space. You have 3 windows, x1, x2, and x3, and then suddenly for a given flux, that is, suppose A1 and A2 are given, because A3 we don't need because they are following these equations, then if L alpha plus beta is less than 1 and the 2 fluxes are positive, so you suppose that this is fixed, this is what the receptor are receiving, and then in that case you have to find and resolve these equations to extract from, so the definition of G30 is G calculated at position x3, it's x3 here, x0. So you have to extract x0 from this, and this is possible. And in general, what you have a system of equation that you can invert to get the probability that depends on f here, which is these equations, J is the Green's function, and B is this matrix that has been inverted. And given the probability, you can find the position of the source. And so this is an example that I just showed to you when you have only one and two source, but when we have three, you end up having two curves that do intersect. So they intersect here at this position, and that's exactly the position of the source x0. If you have multiple sources, like here we have 1, 2, 3, 4, and 5, you are going to have multiple intersection, which give you in some sense some redundancy. So you make sure that your source is located at position x0, and you can solve this numerically. And then what you can also add, if there is fluctuations in the flux, that is, if the flux is not just phi, but phi multiplied by 1 plus a certain noise epsilon, or epsilon is the amplitude, and so you have a certain perturbation, so you add plus minus epsilon, and then you end up having here, instead of having one intersection, you have the intersection of these two bands. And what was interesting here is to see that depending where you are, the surface of this interaction, which gives you the possibility to find the source, here is very large. But you see that if you have the second intersection at 1, it is very small. So this is a very nonlinear effect of where the source is located, depending on the perturbation. So then you have here another example where we have 3. So again, you can have a small region of intersection. Here's much bigger, here it's very large, and here it's very small. And so this is for the case of the ball, where we have here 3 receptors located in an equilateral triangle. So again, I have already discussed this in the case of the plan, but you have the same for the case of a ball. We have 1, 2, 3, 4, and 5, and you have here basically the intersection of these almost circles, which gives you here the intersection, and this is where the source is located. So then you can imagine that from this you can calculate a sort of sensitivity of detection, which is basically the flux at one of this window minus the flux at the other one. And if you have 3, you take the maximum of this difference. And so you can define the region of sensitivity, which is the region where this ratio is above a given threshold. So basically, that said that if the if you are below this this threshold, you cannot sense, you cannot know what's the difference between one source versus the other. And so a direct calculation show that for an optimal window positioning, you can see that this for the case of dimension 2 decays like 1 over x0. And so this is examples. If you put the threshold here at 1%, 5%, or 10%, you see how is the region of sensitivity. And this is for the case we had here, I think 3 windows positioned in an equilateral triangle. If you have here the case where you have only 2 windows, obviously you cannot distinguish what is exactly here in the middle. So there is a cone of where the cell is blind, but outside this cone, the cell is able to identify the difference between the source at these 2 P1 and P2. And so, as a summary of this dimension 2 example, we need at least 3 receptors to infer the source position. The direction sensing is restricted to at most 5 to 20 cell radius, so you get the sensitivity, as we found here, is very small in the free space. So the match asymptotics, what we use here is match asymptotics that leads to this analytical expression for the receptors from a Brownian source. And I would like to refer to the previous YouTube channel about hybrid analytical simulation methods that allow reducing the simulation time step by using this Brownian simulation only locally. And also I will present next week the dimension 3 and how the same approach can be used in higher dimension. Thanks for watching.